Hello and welcome to CPE 350 Chapter 6. Example 12 will be looking at lumped heat analysis applied to a dairy farm. So in this problem, a farmer is required to chill a certain volume of milk to a very low temperature, usually about 4 degrees C, in a very short length of time, and that is to prevent the growth of pathogens in the product. We have the dimensions of a cylindrical vessel in which the milk is cooled, and that cylindrical vessel is jacketed by a heat transfer fluid that is isothermal at 2 degrees C. We're given that it takes 40 minutes to cool the milk to a particular temperature, 10 degrees C, and so the problem asks, what is the overall heat transfer coefficient for this scenario, given that we have the heat capacity for milk? This is a transient problem. It's about the rate of cooling and it involves convection. So we should ask ourselves, can we apply lumped analysis to simplify it? And that's equivalent to asking, is the BO number less than 0.1? To calculate the BO number, we need the heat transfer coefficient between the cooling fluid and the vessel the milk is in, the thermal conductivity of the milk, and the characteristic length. In this problem, the radius is not a bad choice for the characteristic length because that's about the furthest distance that heat would actually have to transfer to convect out of the system. You could also call the characteristic length the volume of the fluid divided by its area, and that would be fine. In general, if the BO number is very close to 0.1 and small changes to the characteristic length put it over, you're probably in a regime where you need to think carefully about whether you trust the answer. Otherwise, there's so many orders of magnitude difference, you don't have to worry that the BO number condition applies. All right, so we don't have any of these well, we have R, but we don't have H or K. Because it's just not given by the problem. And we can take advantage of the fact that a well-stirred fluid mixture is generally isothermal because the mixing actually distributes the heat. And so anything that has no temperature gradient is basically a perfect conductor, or at least it's behaving as a perfect conductor. And so in that case, the thermal conductivity approaches infinity. So if we let the thermal conductivity approach infinity, then the BO number, it becomes 1 over infinity, which is just approaching 0. That is absolutely within the requirements of BO less than 0.1. So yes, we can use lumped analysis for this problem, and probably for any problem that involves a very well-mixed fluid. So what we know now is the initial temperature, the temperature of the surrounding heat transfer liquid. We have a boundary condition that after 40 minutes, the temperature of the milk is 10 degrees. We have the heat capacity of milk, and we have some of the dimensions of the reactor. What we need is the mass and the mass of the milk and the area of heat transfer in order to use the lumped analysis equation. So to calculate the mass, we'll just use density times volume. We'll assume that the density is the same as water, not a bad assumption. And we'll calculate the volume based on the dimensions we're given. So it's basically the area of the circular profile times the height gives you the volume of milk that we're chilling. So something less than 2 meters squared. Now to calculate the area, we have to think more carefully. And this is the area of heat transfer, that is the area of milk that's in contact with the cylindrical reactor exchanging heat with the surround. So it's not the total volume of the cylindrical vessel, it's just the area of the cylindrical vessel where milk is exchanging heat. So that's a cylindrical area and a circular area on the bottom. And to calculate those areas, we have 2 pi r h and pi r squared. And so that's the total area of milk in the vessel that's in contact with the heat exchange liquid on the outside. That's around 8 meters squared. All right, so we can rearrange the lumped analysis equation to solve for U, which is what the question asks for. And we have our boundary condition that at 40 minutes, or 2,400 seconds, the temperature is 10 degrees C. So if we plug this value in for temperature and all of the constants that we've calculated, we're able to determine that our heat transfer coefficient for the system is 383 watts per meter squared Kelvin. And this will be a constant for the given geometry and temperature of surrounds and initial temperature of the system. So what we could use this overall heat transfer coefficient to do is calculate, for example, how long will it take the same system to cool to 4 degrees or 5 degrees. Thanks for listening, and I'll see you for the next chapter.